Question 4. The diagram below shows two identical magnets with their north poles placed close together. On the diagram above, this is A. Draw lines to show the shape and direction of the magnetic field between the magnets. Well, remember, magnetic field lines run from north to south. Because these oppose each other, the lines will not meet. They'll sort of hit and push against each other. They won't add together, they'll just push away from each other. So, and they would just continue to come out with the ones right on the edge, probably going back around to the own ones. But we're only interested in the magnetic field between the magnets. That's the shape. Now the direction, remember, runs north to south, so we have to draw the arrows coming off like so. Okay, and you can do all the rest coming out of the north, heading back into the south ends. You don't have that south ends. B. On the same diagram, use the letter X to indicate the position where the magnetic field strength is 0 and explain why such a point exists. X is right in the middle there, and it's 0 because all of the magnetic field lines pushing themselves away, so they have no grounds for a magnetic field being there, I guess. Yeah, I guess if one of the magnetic fields was stronger than the other, the X point would shift further away from the stronger one and towards the weaker one, but since they are identical magnets, it's going to be right in the middle. Yeah, and because if they were the same direction, there wouldn't be an X at all, because one would, if one was north and one was south, you'd have lines running north to south from the north into the south, and there would be no point where there's no magnetic field. Anyway, let's move on. I think we've done that to there. C. A piece of soft iron is attached to a permanent magnet and then dipped into a dish of iron filings as shown on the diagram below. On the diagram, use letters N for north and S for south to label the poles of the ends of the piece of soft iron. So the soft iron, north is attracted to south, so it's going to become north. That means the opposite end has to be south. Lovely. And because that's connected to the permanent magnet, it's going to become a temporary magnet, and these iron filings are going to be attracted to the temporary magnet. They'll all become little mini magnets themselves. Part 2, the soft iron and the magnet. So the soft iron and the magnet are then moved away from the dish of iron filings. Okay, so we've got two parts here. Let's just detail this with a little bit of colour. So the soft iron and the magnet, there's a magnet and there's a soft iron, they're moved away from the dish of iron filings. So before we even get to the question, we're just making sure we understand what's going on properly here. You're going to have some iron filings connected to the magnet, to the soft iron. Okay, let's keep that really clear. Okay, then explain what happens to the iron filings on the piece of soft iron. So what happens to all these little critters here when the magnet is removed? So we take away the magnet, we've just got the soft iron left. What would happen is the soft iron would lose its temporary magnetism because it needs the permanent magnet from the one that we've taken away to maintain its own magnetism. Because it's no longer a magnet, the iron filings will drop off. Okay. Some of them might stick on because it's never a perfect and fast change, so you may have a small amount of magnetism left behind that'll gradually sort itself out and disappear, but yeah, and as far as we're concerned, it drops off. D. A starter motor in a car is connected to a 12-volt battery as shown below. The total resistance of the circuit is 0.15 ohms. You don't need to know about starter motors or anything like that. It's just a context for this question. You've got K as given, because K is that constant which appears in the equation. B equals K, there's a constant, times the current over the distance away from the wire. This is for the magnetic field around a single current carrying wire. And we're probably going to use the metal frame below. Let's have a look. On the diagram above, draw the magnetic field pattern formed around the metal frame. There we go. At point A when the starter motor is switched on. So key thing here is we look at the plus. We see the plus here. That means the current's going to go flowing around that way. And back up there, back to the negative, because we deal with conventional current. So if the current's going that way, we're going to use our thumb and the right hand grip rule to point in that direction. And we're going to grip it around with our fingers going over and then down the back. Okay, so that's the direction of our magnetic field. Is going to go over and up and down and behind. So up in the front. Draw arrows to indicate the direction. Yep, we don't have to indicate the strength. We don't know the strength because we don't know enough and have anything to compare it to. Next part, part 2, calculate the strength of the magnetic field. Okay, at point B. So it's 0.10 meters from point A. This is point B just up here. So I've drawn all over. When the starter motor is switched on, give an appropriate unit. So we're after B. This is plugging numbers into the formula. Numbers into the formula. Yep. B equals Ki over D. We know D was given as that 0.10 meters. We know I, that was given, or do we know I? We know K anyway, we know D. I, how do we calculate I? We know the voltage and we know the resistance of the circuit. So we can do our I equals V over R. It's a simple series circuit with nothing else going on in there. So we do know I, we can plug all those numbers in and calculate it and get an answer. Now I'm not going to calculate it because it takes more time than you need, but the important thing here as well to add is the appropriate unit with your answer. Magnetic field strength unit is T, capital T for Tesla. So let's write that out, Tesla, or Teslas plural. And I think that's all the questions. There we go.